times vector equals vector, and showing that that's a linear operator. So pick up with that very same thing. Yeah. So we're looking at linear algebra. Just get set up. So the last thing we had was this matrix times vector business. We had a differential equation. And that turned into a vector equation that looked like this. Kx equals lambda x formally. That's what we had. And it was actually from the second order problem with the 2 masses and 3 springs. But the final algebraic problem had this form, and this matrix was a square matrix. This was matrix times column equals a complex number, or a number in general, times that same vector. So that was the eigenvector eigenvalue problem. Okay. And we could have said k times a equals lambda times a. When all was said and done, actually I'm not going to repeat that. I'll just label what we had here, and then we'll continue on. So this was a square matrix, and this was the vector, and this here, the eigenvalue, was just a number. Right, so that's the structure of what we were doing. That had come out of the 2 masses, 3 springs problem. So we're going to see where this can come from. This came from a second order differential equation. What we're going to look at is, and I had shown the linearity property, right? Is that in your notes? Maybe the last thing, linearity. I'll put that here. I think it was, right? So we could have said something like K alpha x plus beta y equals alpha kx plus beta ky. That would be the property of K, the matrix K being a linear operator. So the next thing we're going to do is see in a little more general scenario where these linear differential equations come from. This was Newton's law, 2 masses, 3 springs. So next, this is next, I think it is. We'll look at a differential equation of this form here. Suppose we have dx dt, this will just be a first derivative, but we can reduce higher derivatives to first derivatives. Dx dt is equal to vector f of x. So in that form, it's a very simple equation. But since x is a vector, f is a vector, if we write this out in component-wise, we have dx1 dt equals f1 x1 to xn. And we go all the way down the line. dxn dt equals the nth function there, x1 to xn. So yeah, then we have coupled differential equations. Okay, each one of these variables functions from all the other ones. And this could be practically anything. This could be a very complicated thing. What we're going to look at is the situation where there is, I'll put this here under these conditions, with f of x0 will allow for a systematic treatment. Okay, so again, looks very simple. If this were one variable, you'd say that's a very simple problem, right? And it's n variables. So by the way, this gets a vector on it. So all n of these, right? So then you could say f1 of x1 0 to xn 0 equals 0, etc. Okay, so let's go ahead and tackle this thing. So there's not much more you can say about it at that point. Unless we make use of this assumption here, what we're going to do is expand this function to linear order. Since it says f of x0 equals 0, so expand f about x0. So have we done Taylor expansions of a vector function? Well, it just means we do a Taylor expansion of every individual function there. So that's no problem. So what we have is f sub I of x is equal to f sub I of x0. So now multivariable Taylor expansion, but just the first term. So partial f sub I with respect to x sub j at x0 and x sub I minus, no, sorry, x sub j minus x0 j. Right, there would be higher terms. J equals 1 to n. Provided everything's well behaved and exists. And remember, we were going about that 0 there. And what we see now, because I, we have I equals 1 to n, as well as j equals 1 to n. What we see is we actually have a matrix up here, Fij. So we'll just go ahead and let this, and I'm going to use a couple different things you're going to see. Let Aij be equal to Fi dxj evaluated at x0. And this has a name. This is the Jacobian matrix. And so I'll also show this definition. It can actually just, sometimes you'll see it as capital D F, but we'll put a df vector there of x0. This form indicates it's, matrix of first derivatives as well. So we have all three of these designations. And what that does is it turns this differential equation into a linear differential equation. So since we're expanding about this point x0, we're going to want xj's, or these delta xj's, to be small. Okay. If they're small, then we're going to truncate this differential equation. And what we'll have is the linearization of this array of differential equations right here. Let's put this in some good form. And so I'll put under here and I'm just going to use the letter y. Y sub j equals xj minus x0j. So this y sub j is a small quantity. Let that be small. And notice that dy sub j dt equals dx sub j dt. Ij was in the name here. Let's use I for this. Not that it matters. I. Okay. actually a process we've done often in various situations. So yeah, if we put all this together, I'll just take that square there in the board. We're going to have the linearization of this differential equation. And we're going to have, okay, so now dy sub I dt equals the sum over a sub I j y sub j. J equals 1 to n. And since a sub I j here, this is that square matrix of first derivatives, Jacobian, we could also say, right, and this goes down from I goes from 1 to n, so we could also say we now have a differential equation matrix times vector. So this again shows how general this situation is. Derivative of your vector is the matrix times the vector. And based on what we just did before, it's linear operator, vector, linear operator. Good, so yeah, this progression is important to recognize. You had this differential equation, you had a point where f of x is 0, and because of that, we were able to expand around that point. And as long as we're close to that point, so this is a small quantity, then what we actually have is a linear differential equation. And this linear differential equation with constant coefficients, let's make sure we write that up. Linear differential equation with constant coefficients. So as long as we have that, we can solve this. Okay? In fact, it turns into a linear algebra problem. So let me go ahead and erase this. N's an arbitrary integer, but n equals 1 is the one we want to talk about first. Okay, so if we take the case where n equals 1, yeah, then what do we have here? dy dt equals a times y. A is just a number, could be a complex number. What's the solution to that differential equation? The all-time basic differential equation. Y equals y sub 0 e to the lambda t. Is that our ansatz? Lambda y0 e to the lambda t equals a y0 e to the lambda t. Lambda equals a. Okay. Lambda equals a. Therefore, y equals y0 e to the a times t. So yeah, that's your very basic differential equation. We could have done separation of variables in the logarithm and gotten this out as well, right? But this is, we've done this often enough. So what's interesting is this form holds true all the way into the world of operators and matrices. Okay. So what we'll do next is the case n is greater than 1 and see what happens there. Go ahead and make up some room here. square matrix, dy dt, vector A is equal to the matrix Aij. So the solution is going to be y of t equals vector y sub 0 e to the lambda t. And we have to see how the linear algebra plays out on this one now. So we're just going to take this as a trial solution and write the solution as a vector e to the lambda t. And we take this into this differential equation. So I want to make sure I separate these two steps so that dy dt is equal to lambda y0 vector e to the lambda t. The a times y is equal to a times y0 e to the lambda t. But e to the lambda t is just a number. A is a linear operator. So we can pull the e to the lambda t out. A times y0, matrix times vector. So when we equate these two, we're going to have lambda, let's write it in the, we'll change the order here. So we're going to have e to the lambda t, and then lambda y0, that vector, equals e to the lambda t, a y0. And what we see from this is just a number, cancels on both sides. Then we have the eigenvalue, eigenvector equation again. Okay. So what it means is, on our way to solving this differential equation, we have to solve the eigenvalue, eigenvector equation. Okay. So that comes up again, right? That's where it naturally just comes up that you have to solve the operator equation, eigenvalue times eigenvector equals matrix times eigenvector. Yeah, so we've arrived at this a couple of times now. So eigenvalue and eigenvector. So yeah, now we have to consult the mathematicians on matrices, eigenvalues, and eigenvectors. And they've taught us a couple of techniques on that. I think we had mentioned that the other day. So we've got this again, this whole complex. And the way we solve this is we take the determinant of A minus lambda times the unit matrix set it equal to 0. And that gives us the characteristic polynomial. This expression is the characteristic polynomial. And from that we find lambda sub 1 all the way to lambda sub n set of eigenvalues. So I'll number these steps here. And what's the second step? Sometimes you just declare victory right there because that's all you wanted. Okay? But what if you got to move on? Or what if you got to complete the problem? Then you take these eigenvalues back into this equation, and since they're now known, you can solve for the eigenvectors. Okay? So take the eigenvalues I'll just call them A sub lambda. So our eigenvalue, we could say A times A sub lambda equals lambda A sub lambda, where this eigenvalue is now known. So that's the process. Let's see if we have a good example for this. Concrete example. Okay, so this was the whole eigenvector, eigenvalue problem. Let me go back to the second order differential equation, because a nice example is again masses and springs, because we can completely visualize the masses and springs and their eigenvectors. Not their, well, some of the eigenvectors. This is a good physical example from 105B. I'm taking it out of order. Okay. So here's the example. It's actually from a second order problem like the other one was. I'll write here examples and just remind you. So the 2 masses and 3 springs. Did I bring the double pendulum to class yet? Maybe not.
Not this one.
Not this one, yeah. Okay. Doesn't matter. This can be visualized very nicely. So this was our 2 masses and 3 springs. We call them K, M, K prime, M, and K. We had no friction. We were on this x-axis. This was our x1. This was our x2. And the eigenfrequencies, or the eigenvalues, had to do with these 2 possible motions. Okay. So yeah, this is actually review. Then we'll do a 3 masses and 4 springs example. So what we had was x1, x2. That was our vector x. x1, x2, and if they were moving together, then we saw that the middle spring was not even being worked, right? The middle spring was not being involved, and so because of that, we knew that omega squared was just k over n. But if, but if they were moving against each other, right, then this middle spring was coming in with twice its strength because it was half a string, and we were getting omega squared equals k plus 2k prime over n. So here we have the eigenvalues multiplied by m, we have the two different eigenvalues, and we have the motions that go with it as being the eigenvectors. So that's why this is the all-time example for identifying, motions, eigenvalues, eigenvectors. And we had done this, if you look at your notes, we had done the 2x2 matrix on this and everything. Okay? So here's what we're going to do. Let's just generalize this and see if we can recognize anything. Okay? So this time we're going to take equal masses and equal springs all the way down the line. Next semester we'll do a lot more with this, but so there's our x-axis, equal mass. So now just we have equal springs k everywhere, so we can solve this thing. And we have x1, x2, x3. Now we can no longer have this thing moving together with the other ones. Okay, but there is still one thing that the symmetry shows us that we can have. We could have the x1 and the x3 moving against each other, right? And leaving this one in place. So that's definitely an option, right? So the analysis is going to show it to us, but we've got x1, x2, x3. And when everything's relaxed and they're at rest, that's, x is equal to 0. So one of the omega squareds, what would you guys say it'll be? The math is going to have to deliver it. But what the physics tells us, right, if this one's nailed down and these other two are just moving against each other, what would the frequency be if this one's nailed down? Just ignore the one on the right, because this one in the middle is nailed down. What's the frequency going to be? Omega squared. Single mass, single spring is k over m. This time that spring's just acting as a full spring, so it's 2k over m. So you're going to get this, as we set this problem up, that's going to be one of your eigenfrequencies. We can see what the eigenvectors also, we can also see what the eigenvector is going to be. Because again, if this thing's nailed down, these two are moving against each other, we're going to have A sub whatever. It's going to be this one at rest, so it's going to have a 1, 0, minus 1 structure to it. I'm not talking about the normalization of it. Because when this one's moving forward, this one has to be moving backward. Okay? And they're both being, or it's being multiplied by the same either lambda, omega squared t. So that's as much as we can guess on physical grounds. Now the other eigenvalues, well, we're going to work them out. We'll work them out and find them. So this will be a good one. Let me see how much of this I should give away. So we'll set this one up as a homework problems. Yeah. I have here in my notes, I have the stripped down version without the factors in here, but you know what, we're going to do it with the mechanical quantities. There should be a way to camouflage it. I could camouflage this thing with numbers, and we wouldn't even know where it came from. Then it would just be a bunch of numbers and eigenvectors. We could do both. Okay, but yeah, that's the physical problem. I'm going to erase this and open up some room. I'll show you where both of these come from, okay? The physics we're going to do more systematically. I can just write it as a math problem, but let's do both. So, from mechanics, potential energy is going to be a half K x1 squared plus a half K x2 minus x1 squared plus a half K x3 minus x2 squared plus a half K x3 squared. So those contributions that I've written down are simply the individual springs. So this first spring here only knows about x1. Okay. The second spring only has energy in it if, you know, x1 minus x2 is non-zero. The third spring has to do with x3 minus x2, and the fourth spring only knows about x3. So that's how you add up all the kinetic and potential energies. The matrix, the eigenvector eigenvalue problem would be k x equals lambda x. That's if you actually have to know to skip steps here. From the equations of motion, we're going to get kx equals lambda x. So Newton's laws, or in this case, the Lagrange's laws, are going to give us kx equals lambda x for this 3x3, or three particle problem, just like we had it for the 2 particle problem. And k is going to be equal to 2k minus k, 0 minus k, 2k minus k, and 0 minus k, 2k. So I'm going to erase this and make up some room now. So now I'll write homework, find. So this will be for next week, right? We'll put this first one on next week. So find eigenvalues and eigenvectors for this problem. And we already just listed what one eigenvalue and one eigenvector, what we expect to get. So that should help us out. Motion is just for the record. I'll write here Newton or Lagrange. We get this. What I was going to do was skip this whole thing and just give you guys the numerical version. But actually, if I put both of them up here, you'll see why we're so glad to be physicists and not learning this in a math class. Okay. Here we actually have a handle on everything that's going on. I didn't tell you this derivation of the equations of motion for this problem, but I did for the first one. The first one we did step by step. We didn't skip anything. Okay. But so yeah, find the eigenvalues and eigenvectors, and I'll put here as a note the numerical, or not numerical, but the stripped down version that I was going to give you. Well, I thought better of it. I just wanted to give you this thing here cold turkey. 2 minus 1, 0, minus 1, 2, minus 1, 0, minus 1, 2. Right? You recognize this as being this, but this is the actual physical problem. If you looked at this, you're not going to know what your eigenvalues and eigenvectors. They're not gonna have that intuition for what's even going on in there. Okay? But this would just be the version with, and find eigenvalues and eigenvectors. So this is how you encounter it in math class possibly for the first time, and it just remains less concrete. Whereas we've got this picture of the oscillating mass on the board. That's where this problem came from. Right? Everybody sees this thing right here. So you can tackle that away. Right? At this point, it's been stripped down. And because it's a symmetric matrix, with real coefficients, it has certain properties as well. Okay? So you're not just going to guess the eigenvector and eigenvalue the way we were able to do on physical grounds. So I think that's a point worth making. So yeah, the homework problem refers to this. And yeah, good. Let's see. So that'll be for next week. That was the first one for next week, right? So let's see where we can take this. That's a good way to segue to other stuff. Another great idea. Let's see. Well, let's start this one. Everybody remember how to set up the characteristic polynomial? Let's do that. Just to make sure. So suppose we're going to do the next step on this problem here, and this one I'll erase, but keep this one in mind. You can also just try it with the numbers. There's another advantage to having quantities with dimensions on them. If you find some dimensionally impossible expression in your work, you realize, oh, I made a mistake, you gotta go back and find it. Whereas with the numbers, you can just keep pounding away until the end of time. Okay, so the next part of this problem would be the characteristic polynomial. And we're looking for eigenvalues that we're just going to call lambda. So we've got k minus lambda times the unit matrix. When the determinant is equal to 0, that's how it's the unit matrix 1. Okay? That's how we're going to find eigenvalues. Eigenvalues are going to have dimensions. What it's going to be? It's going to be the dimensions of the k, right? So the lambdas are going to be some kind of m omega squared. But they're not going to explicitly have that right here, okay? Because we didn't do that part of the. We'll study that later. So how do we set this thing up here? There's k minus lambda times 1. That means we're looking at the determinant of 2k minus lambda. That's the first corner. We're subtracting lambda off the diagonal. Minus k 0 minus k, and then again 2k minus lambda minus k, and I'll put parentheses around those, 0 minus k, 2k minus lambda. So that's the determinant that we're looking for in each of these. Right, that's those are on the diagonal. So you expand that out, and just looking at that, you're worried because there's cubic, but something's going to factor out nicely on this one. Okay? there'll be some, something that factors out that, leaves you with quadratic, and you're not gonna have any problem with it. Otherwise, it would be cubic, right? You're gonna have lambda cubes there. And if you have something that's principally just a cubic, you just hang up and go home, right? That's not gonna be easy to solve. Maybe I'll put in here for the record. From mechanics, it would be determinant of k minus omega squared m times 1 equals 0. So if you want, you can take the lambdas that you find and call them omega squared m. Because it came from an oscillation problem, where it really came from. But if we just had that array of numbers, we would just stay with the numbers that are there. Okay, that's enough for that one. Let's see what else we can get going on. So I want to relate it to the linear algebra we just did, okay? So this is the task of finding the eigenvalues and eigenvectors. So now you found them. What does that mean for the general scheme of things? Okay, so it's a good problem. Did I write homework on this one? I think I did, right? This one was the homework to complete this one. Okay, I'm going to erase this. These are some of the all-time good examples if you want to visualize what all this stuff actually means. So here I'm going to write, after eigenvalues and eigenvectors, then what do we have? Okay, then we have to look at the general solution. So after finding eigenvalues slash vectors, question mark. So now let's go ahead and look at our differential equation. We'll just call it in this form, x, y, doesn't matter. A times x, x was x1 to x10, right? So we're back to that problem. Now we have found the eigenvalues and the eigenvectors with, I'll say, lambda sub j with a set of lambda sub j, a sub j. So that's a set of eigenvalues and eigenvectors. So what does a general solution look like? Anybody remember? General solution to a linear differential equation. You have all these things, got a whole set of them. What comes to mind? We already, well, the solutions are, we already know that. They're all some kind of exponential function. So how do we combine them? That's a real hint. What comes to mind is linear combination. Right? You guys have heard that before. So we need a linear combination of these things. The general solution which I'll also call x of t. It is a sum, a linear combination, because remember that it's a linear differential equation. If you take a sum of these things, apply the operator to them, it's going to still be a solution. So what we're going to call this is alpha sub j, a sub j, e to the lambda sub j t. J equals 1 to n. So that's a linear combination of vectors. The alpha sub j and the e to the lambda, alpha sub j is complex numbers. So alpha sub j are complex. Of course, the lambda sub j are also complex. That's just a string of vectors, and because we have this linear property, if we take the derivative of this, okay, we're going to have alpha sub j, lambda sub j, a sub j, and then when we apply the matrix to that, it's just going to come out as a linear answer to that, okay? So the linear combination, let's actually make sure we have that terminology in our notes. Linear combination. So we can actually write this thing as a vector as well. Okay. We can write this thing as a vector matrix equation. So what would that look like? The left side we would have x1 of t all the way down to xn of t. We'd have a big column vector. And on the right side, we have to be careful here, but for the moment, I'll just write out, we'd have alpha sub 1, vector a sub 1. I'm going to fill this in a minute. E to the lambda sub 1 t. And we go all the way out here, alpha sub n. This would be the a sub n. E to the lambda sub n times t. But since this is going to be a matrix multiplication, we can organize these things. We can think of these eigenvectors as column vectors. I'm writing too big, but see if I can fill that all in right there. You can think of these eigenvectors as column vectors. So what I'll do is I'll label it up here. Okay, and as column vectors. And then how would I label these columns? Then this would be A11, A21, all the way down to AN1. So A1N, all the way down to ANN. So I'll put this as a note for you guys. Eigenvectors as columns. So then the question is, how are we multiplying this now? Looks like we've got a matrix, and I'll write it over here now. Got our general solution. So let's see, we would have x equals a matrix. I'll do this once more slowly. X1 down to xn. So now we've got A11, A1n, AN1 to ANN. And what's in my column here now? I've got alpha 1e to the lambda 1t, alpha 2e to the lambda 2t, all the way down to alpha n e to the lambda t. So now I have the solution x matrix times vector once again. And now you could consult with the mathematicians and ask what's the inverse matrix of this, and then I could peel out a vector that only depends on the individual frequencies. Right, if we have, or if it exists, the inverse matrix, I'm just going to call it A inverse. So A right now, this lowercase a is a matrix, then A inverse applied to this x is equal to this column, which is just each of whose, I'll just write this, alpha 1 e to the lambda 1. You remember these alphas were arbitrary constants, right? Arbitrary constants. Alpha n e to the lambda n t. Suddenly we have a vector, each of whose coefficients has one frequency only. Okay. So this is a huge simplification, because this original one here that I wrote out, each component right here is a sum of n different frequencies, right? There's nothing you can even see going on there, although it's a true and linear solution. This transformation gives you individual frequencies for each component, at the cost of having to invert a matrix instead of choose poison. But this will take us to the normal modes. So yeah, if you're just studying this without the physical background for it, it's just going to be much more difficult to understand. Here we can actually, especially if we refer back to our 2 and 3 mass problems, we can actually see in our mind's eye what's going on. Good, so I'm going to leave it at that, and we'll do the operator stuff next week. Okay. We'll do the operators. But we definitely have to have a